Very good morning and warm greetings, dear friends and students. Today we are going to see the cylindrical shell or the thin spherical shell problem. The case of thin spherical shell, when the thickness is very small compared to the diameter, that's why it is called as thin spherical shell. Here the hoop stress and longitudinal stress are denoted by F1 and F2. In the case of thin cylindrical or spherical shell, the F1 F2 value in the case of thin cylindrical shell is different, but in the case of thin spherical shell, the hoop stress and launch stress are equal because of the spherical in nature. Now we are going to see a problem in thin spherical shell. A thin spherical shell of diameter 25 centimeter is subjected to an internal fluid pressure of 10 Newton per square millimeter, and the thickness of the shell is 5 mm, and the Poisson's ratio of the material of the shell is 0.3, and the Young's modulus is 2.22 into 10 per 5 megapascal. So what will be the major principal stress and minor principal stress in the case of thin spherical shell? So sigma 1, that is equal to F1, that is equal to PD by 40. So this is how we have to find the hoop stress. Here the hoop stress is equal to major principal stress. So that is equal to 250 into 10 into divided by 4 into T thickness is 5 mm. So if you are giving the solution for this hoop stress, you are working out, you are getting around the value of 125. So the value of the major principal stress sigma 1 is equal to 125 Newton per square millimeter. So what about the minor principal stress or minimum principal stress? So it is denoted by sigma 2. So in the case of thin spherical shell, F2 is equal to PD by 40. Again, it is equal to F1. So sigma 2, that is equal to F2, that is equal to pressure is 10 Newton per square millimeter. So 10 into 250 divided by 4 into 5. The thickness is 5 mm. We are getting the F2, that is the longitudinal stress. The case of thin spherical shell is, we are getting the solving of this value, we are getting 125 megapascal. So here the hoop stress and line stress are equal. So therefore F1 is equal to F2, that is equal to PD by 40. So we are getting 125 megapascal or Newton per square millimeter. So therefore, what about the maximum shear stress developed in the case of thin spherical shell? So tau max or Q max is equal to the average of the difference of the major and minor principal stress. So that is equal to half of sigma 1 minus sigma 2, that is equal to 0.5 into 125 minus 125. So because of that, there is no shear stress at anywhere in the section of the thin spherical shell. So we are getting 0. So there is no shear stress at all in the case of thin spherical shell. But in the case of thin cylindrical shell, you are getting a maximum shear stress. So because of the geometry of the cylindrical shell. Here, wherever you take the cross section is either inclined plane or a horizontal plane or a vertical plane. In the case of thin cylindrical shell, you are getting only the circular in cross section. So either a cross sectional view or the front view or top view, whatever it is. So there is no shear stress in the case of thin spherical shell. So that is the major advantage of thin spherical shell compared to thin spherical shell. So it will take more pressure and the thickness required is very small, and also there is no maximum shear stress compared to thin cylindrical shell. Thank you very much for patient listening. God bless. வாழ்க வையகம் வாழ்க வளமுடன்.